Okay, so while the speaker is setting up, I'll do the intro. So welcome Arjen Jakobi. He is associate professor in the Department of Bio-Nanoscience and leads the electron nanoscopy group at the Cavilli Institute in Delft. Arjen did his PhD in Leiden and postdoc in Utrecht in structural biology and single molecule biophysics. He then moved on to a postdoc or EMBL using cryo-EM to investigate protein assemblies involved in autophagy. In 2018, he started his group in Delft and has lots of exciting topics on membrane remodeling, autophagy, biomolecular assemblies. But the reason why he's here for this session is on methods development in cryo-EM. And he's been working on density interpretation and sample preparation and is going to be telling us about the new exciting studies in LocScale. Thank you.
Thank you, Dorian, for the introduction, and thank you to the organizers for inviting me here and having the opportunity to present LocScale2, which is an extension of LocScale1, obviously, and try to give you some hints on what has changed and why we think this may be useful for the community. To start off with, let's just remember that in cryo-EM, through experimental and computational factors, we have resolution-dependent attenuation of the signal, which leads to contrast loss at high resolution. So if this would be the structure we actually want to image, this may be the image that we're getting out of this. And we measure this attenuation as something that we call a B factor, which is an aggregate factor that just describes the steepness of the fall off of the average Fourier amplitude as a function of spatial frequency or resolution. Now, in order to come back from this blurred state to what we call a sharper state, we need to do something that we call B-factor sharpening, and that's a method that has been proposed both in X-ray crystallography by Axel Brunner and by Peter Rosenthal and Richard Henderson for EM, which basically just tries to undo that blurring operation by using a negative of this B factor and then basically scaling up high resolution or the signal at high resolution or high spatial frequencies relative to the low resolution frequencies. And if we choose that B factor correctly, then we essentially get back the original image, provided that we also apply a filter that accounts for the signal to noise ratio, because we of course are not just scaling up our signal, but we are equally scaling up the noise contributions at each spatial frequency. Now in EM, it's very frequently the case that the resolution is not uniformly distributed across the map. So we have resolution variation, and that means that also our B factor locally varies. And that was the inspiration of LocScale1 to basically provide a way to locally compensate for that signal loss or contrast loss at high resolution spatial frequencies. And it was inspired by the fact that we have a very robust way to estimate this, this local variation in B factor by using atomic displacement refinement for atomic models. So provided we can somehow fit a model into the map, we can then estimate based on the simulated map from that ADP refined atomic model in a local window, the spatial frequency dependent fall off of the radially average structure factor, and imprint this on the original reconstruction. You can see that for one of these windows here, and that basically leads to a locally varying scaling scheme. Now, that works very well, but it comes with an obvious problem that we need an atomic model. And in the first place, the reason why we are trying to optimize these maps is to build an atomic model into these maps. It comes with another problem, and that is if our experimental model is incomplete, then if we're using this model to scale our experimental density, this will lead to attenuation of densities that are not being modeled by the atomic model that we've placed into this. So you can see that here. We've placed an incomplete model into this map, and then you see that at the, in this case, extracellular region of this trip channel, densities are being scaled down. At the point where the atomic model has been fitted well, the density is scaled appropriately. Now, you can partially recover this in principle by then using that optimized map to extend your atomic model and do this in steps. which eventually leads you to a completed model, but there's no guarantee that your final model is complete. And obviously that's not really a very efficient procedure. So that's not great. And that's why we posed the question if we can do reference-based sharpening without an atomic model. Now, there are other ways how you can do local sharpening without atomic models. I'm not going to discuss those, but I'm going to come back to them later. But in our case, we really want to do this reference-based. So we want to have an estimate of that radial structure factor and imprint that onto the experimental density maps. Now, in principle, how this radial fall off of the radially average structure factor looks like as a function of squared spatial frequencies is very well known. So we can compute this from many, many different structures that have been deposited in the PDB. And it basically has a number of different regions that at the low resolution end describes the contrast between the molecular envelope or the boundary, molecular boundary and the solvent. And then at higher resolution, we get contributions from the individual atoms, and there are some bumps in that fall off that correspond to secondary structure, because secondary structure has certain repeats in real space that basically leads to an amplification of that amplitude at the corresponding spatial frequencies in reciprocal space. So the core idea of what we try to do in LocScale2 is to estimate that radial structure factor. And to do that, we need to do a couple of things. So we need to have a way to estimate, a robust way to estimate the molecular boundary without knowing anything about the molecule that we're looking at. And I'm showing this here in a way where we still have partial model information, but it holds true for regardless of whether we have any of this information available or not. So the first thing we need to do is to estimate that boundary, and we do this through false discovery rate controlled statistical tests. So for each voxel in our map, we basically do a test on whether that voxel intensity falls within a background noise distribution or not, and then we assign that to being signal or background. And that works very, very robustly. So we get typically very robust envelopes. You see that it contains the entire protein structure, in this case also the detergent micelle. So that gives us the boundary and the total scattering volume that we need to model, which basically corresponds to that very low resolution part of the radial structure factor. Now then we fill this with a pseudo-atomic model. So we form a pseudo model where we're placing average atoms that represent the structure that we try to model, that basically helps us fill that total scattering volume and determine the scattering distribution or the distribution of atomic scatterers, which covers this part of the radial structure factor. Now then we know from prior knowledge what this structure factor approximately should look like on average for a protein or for detergent micelle or whatever for nucleic acids, whatever you want to model in your protein. So we can use this to imprint it on this pseudo model. And then we use the pseudo model in a restrained atomic displacement factor refinement in order to get the local variation of the B factor in that structure. And then we can use the procedure in the same way as I showed you previously. So I'm just going to show you quickly what this looks like. So here we see the coordinate refinement of the pseudo model. Initially, they're just randomly placed in that molecular envelope defined by the FDR mask. And then it's using the potential of the map in order to refine the position of these atoms. And you see, as we are going through that refinement, they start to resemble the outlines of alpha helices, for example. And you see that also if you look at the structure factor that now approaches more and more the expected structure factor that we would have from a typical protein model. Now, once we have that, you can see that here after several cycles, we need to refine the atomic displacement factors. And you can imagine that you need to find a way to regularize this refinement because otherwise there's a high chance of overfitting to your data. And I can't go into the details of how we are doing that, but Alok is here. He has a poster. I'll mention the number later, and you can talk to him about how we are doing that. Now you can see that if we do this, then you see the fit of the model to the map increases. So we are improving the representation of the experimental density map. And you can also use validation tools to show that we are not overfitting this distribution. This shows the distribution of B factors that we know should follow an inverse gamma distribution, and it does. And this shows the half map refinement, where we refining our model against one half map and testing against the other half map that should basically follow a similar trend to indicate that we are not overfitting to our data. Now, once we have this, we can put this together into a scaling procedure similar to what I showed you before. We call this hybrid LocScale. So the steps are as follows. And we start with an unsharpened map that's typically the sum of the unmodified half maps. And we determine the molecular envelope. We estimate the local B factor distribution through the procedure I just shown you. And that gives us a scaling reference. And using that scaling reference, we can scale the original map, and that gives us a locally sharpened map. Now that works fairly well, but it's very slow. So the whole procedure of placing the pseudoatoms, refining their positions and the ADPs takes long. And we know all of you are very impatient. So even if it's 20 minutes versus 1 minute, you will never use it if it's 20 minutes. So that's why Alok tried to perform this procedure on a large number of maps and then train a network to basically predict the scaling reference from that large number of training data. And you can look at the amplitude correlation of these individual cubes as we would get them from the network that we're calling EMANET, compared to the amplitudes that we would get if we use this physics-based scaling procedure. And you see that the amplitude correlation is very good across the entire spatial frequency range. So what you can do now is you can basically just give the network your map. It will predict the scaling reference, and then it will use that scaling reference to scale the original density map, and that leads you back to the sharpened map in a procedure that is much faster than the physics-based approach. Now, does this work? This is just comparison of a few structures optimized using LocScale2 or LocScale1. LocScale1, again, is a model-based approach. So everything is restricted to the model information that we have provided. And now you see for LocScale2, the quality of the improvement in the map is similar, but we also get contextual information. For example, we are getting low resolution representation of the detergent micelle. And then this is a particular case of gamma secretase where in the model-based scaling procedure and deep learning procedures, you lose density for one of the transmembrane helices, and here it's coming back. At least you can see it. This is another example just to show you that it efficiently recovers contextual information, but at the same time doesn't compromise on the detail that you can get in the scaling procedure. And you can see that probably best here, where you see a scaled map together with its detergent belt. But if you zoom in, then you see that in the interior, it preserves all the detail that you would expect. So that's nice, but the question is that useful? So we asked the question on whether such maps could help automated model building. So we tested this on Model Angelo. And actually, our initial expectation was that probably it wouldn't be any better because Model Angelo has not been trained on any such maps. But what we found is that typically, if we input these maps, there are always stretches that Model Angelo can now build in addition. This is another example for nucleic acids. If we are looking at that as a function of, or for a large number of EMDB entries, and we compare it to how Model Angelo builds into the deposited maps, then we can compare this for Model Angelo output before pruning and after pruning. So after pruning means that Model Angelo is already correcting for or discarding residues that it can't build residue stretches from. We still see that for quite a number of maps, we can improve the coverage of the model quite significantly. So that suggests that maybe if we would be using such maps to train automated model procedures, we could improve the coverage even more. Now, the question arises that I showed you that we're using these predictions to scale the amplitudes of the original maps, the question arises if we cannot use these predictions directly. And there are two methods and some others that came up recently that are actually doing exactly that. So these are deep learning based methods that basically have been trained on experimental and for DP enhancer LocScale1 target maps, or for EM ready experimental maps and simulated model maps. And then these predictions give you nice looking maps that are sharpened, and yeah, more than that, also modified the phases, because you need to remember that whereas sharpening only affects your amplitude, so maybe paradoxically, while your map looks better, the resolution of that map has actually not changed. If you use these methods, it's more similar to density modification, where you're changing both amplitudes and phases of the predicted maps, because those are trained in real space. So it's a real space mapping that is being done. And you can see that also. So if you're looking at the correlation of amplitudes, then you see that these methods actually predict amplitudes really well. If you look at the phase correlation to the original map, then you see that the phase correlation, especially at high resolution, is actually very poor. So that suggests that there is a risk that in these density modified or these deep learning modified maps, there is a risk of phase hallucination. So that doesn't mean that those methods are not useful. I think they are. But we need to think about how we can validate those predictions. And we maybe also need to think if we are taking these deep learning predictions sometimes too lightly. They look very nice, but not everything we see in them is necessarily real. So we thought about whether we can not combine the deep learning based prediction that we have developed together with a reliable filter that we have. So that's the amplitude only filter, and basically use these pairs of maps as a measure to determine the confidence in our prediction. So the question is if that maybe is a way to have a more objective way to evaluate the deep learning based predictions that we are getting. And I'll try to explain you in a few words how that works. So what we are doing here is basically use the same network that I've introduced before, but now we perform something that's called variational inference. So basically during inference, so during the prediction from that map, we're using a dropout technique. So that means we randomly drop out some of the nodes in the predictions of the network, which gives us a number of predictions. And from that, from this range of predictions and its variance, we can determine the distribution that we are expecting for each voxel position coming from that prediction. Now, if we calibrate this, we can convert this into uncertainties, so predicted uncertainties of our network. And we can use each of these predictions as a scaling reference to perform a log scale map scaling, which is just an amplitude modification procedure. And then we can look at the intensity distributions in these log scale maps and do a comparison to the predicted uncertainties that we have derived from our network predictions, and then compute a score that we call a predicted voxel-wise difference test score, and map this onto our predicted map. And this map we call a feature-enhanced map. And at each position of that map, you now get a measure of certainty with which you can trust the prediction of the network that the network has made. And it doesn't mean that anything that's red or blue here is wrong. We don't know. We just know that it significantly deviates from an amplitude-only modified map. So it's an abstract way of measuring the phase error of your predictions. Now, is that useful? We can look at some examples. This, for example, is translating ribosome. You see a DP enhancer map here, and you see the FDR determined confidence boundary around it. And then we see the log scale predictions. And we can see that, for example, we're now recovering density in the A side tRNA. We also get some density for a nascent peptide that's emerging from the ribosome. Another example you can see here, so you can scale this down all the way to ligands as well. This is an example where we have a ligand-bound structure, and you see the deposited map, which in this case was a DP enhancer modified map. We see the feature-enhanced map that looks very similar, but now for each part of that predicted map, we also get a confidence score on how trustworthy the predicted density actually is in those regions. So I don't know the answer whether it's useful. I think you have to figure out and tell us, but we think that it may be useful. Another example, just to show that the difference, I think, between LocScale2 and at least two other of the deep learning-based map modification methods is that LocScale2 tries to preserve contextual information, and that's one example that you see here, where DP-Enhancer and EM-Ready, which have been trained on model-based densities, either implicitly by using LocScale1 targets or by using explicit model information. In the case of EM-Ready, they recover the well-resolved high-resolution part, but not the low-resolution parts of this density map. And LocScale2 will also scale the low-resolution density parts without really compromising on the detail that you have in the high-resolution parts. And that may be more important for samples that come from complex mixtures or in situ samples where, for example, you have membrane-bound complexes. So that's an example of a subtomogram averaging of the COP2 code, where you see the deposited map and you see the LocScale feature-enhanced map. Where the feature-enhanced map, you preserve the detail in the high-resolution structure, but you also get the contextual information from the membrane. So that's what we're trying to achieve with this method. Now, in a nutshell, this is how it looks like. This has all been developed by Alloc, so it should not really be called LocScale, but probably should be called LocScale. And in summary, it combines a physics-informed map optimization with a deep learning network-based map optimization methods and try to combine these two in a useful manner to predict a score on the confidence of the prediction. And all of this is now also implemented in CCP-EM thanks to Agnel. As I said, it comes in different flavors. So there are different ways how you can run LocScale, and some of these flavors may be most suited for your method. If you want to learn more about this, you can look at the documentation, which I hope is complete. There's a preprint underway. Maybe next week we can finish it up. Now, I want to end off with something else that Alloc recently developed. So sometimes that contextual information is extremely useful for interpretation, but for visualization, it's nice to have both the representation of that contextual structure and the representation of the density map without that contextual structure. So he trained another network that he calls LocScale Surfer, which basically tries to segment these low resolution densities. And he made a camera plugin that basically allows you to toggle on and off between these different representations. Under the hood, what it does is it tries to do a segmentation and then a filtering of the segmented densities based on some geometric considerations. And eventually this all ends up in a simple camera plugin where you just load your unsharpened map and your confidence mask that you have predicted from or that you have computed in your LocScale job. You segment this and then you can apply, in this case for removal of detergent bells, you can apply this to your feature enhanced map, and that gives you these two representations. And there is a toggle switch that allow you to toggle on and off between those. Now, currently, this is limited to detergent micelles, but there's no reason not to do this for other contextual information, more complex membranes, and that's something we'll be looking at in the future. So with this, I just want to end up with thanking everyone who has been involved. So Alloc has been the leader of this. He has a poster also in the first poster session, poster number 7, and he's been working closely with two master and bachelor students, Rainier and Lotte, who have been involved in devising the Eminet network and the LocScale Surfer camera plugin. Much of this has been in discussion with people at MSc LMB and UKRI, CCP-EM. So Agnel has been putting all of this into CCP-EM Doppio. Rangana has been helping in implementing symmetry averaging using his EMDA tools. Keitaro has been involved in devising the regularized ADP refinement while he was at the LMB. Now he's in Osaka. and Chiara has been discussing with us about Model Angelo. And the documentation and tutorials online, and the code is available as well. And the preprint will hopefully come soon.
Thank you very much. I'm going to take chair's privilege and ask the first question. How does LocScale2 kind of handle glycosylation and the fact that these sugars are much more mobile than amino acid side chains in terms of your physics-based model?
Yeah, so if you use the physics-based LocScale approach, it will scale those glycans appropriately. It will not improve the representation of these glycans in the sense that it doesn't magically make them recognizable, but it will display the densities that are associated with it. And the feature enhanced maps will do the same because they have been trained on a large set of data that also contains these kind of post-translational modifications. But whenever you are looking at something which you doubt that it's contained in the training data set, you should always use the physics-based approach. And that's agnostic to what is the underlying structure. It will just estimate the molecular boundaries. So whatever is detectable as signal will be scaled as such.
Thank you very much. And questions from the audience? Yes, in the back there. Let's go down here first because you're already here with the mic. Save you on the running.
Oh, thank you. Really nice talk. Thank you, Arjen. You mentioned that the B factors are being modeled as an inverse gamma distribution. So we know that different regions, B factors follow different shifted inverse gamma distributions. Have you tried optimizing mixture parameters?
Yes, we have been looking into this. So I encourage you to go to Alex poster. You can show this. Yeah.
Now we've got at the top.
Hello, thank you for a very nice talk. I'm wondering, do you calculate difference FO minus FC maps as well?
If we calculate
difference maps between observed amplitude, observed structure factors and like calculated structure factors based on model. Is it possible? Could you comment?
It is possible. You need to scale maps appropriately, then you can compute difference maps, but it's not something we do within LocScale.
But it should be possible.
It is possible, but we're not doing it. Yes.
Yeah.
Okay. Other questions from the audience? Didn't see any on Slack. If there are no other questions, I just have a couple. Oh, first, let's do thanking of the speaker. Thank you, Arjen.